Okay, welcome students to our fourth lesson on covalent substances. We're going to look at the observable properties of vapor pressure and solubility today and relate them back to those intermolecular forces within a covalent molecule, or between molecules I should say, so those dispersion falls, dipole interactions and hydrogen bonding. So the first one I would like to discuss with you is that idea of vapor pressure and a vapor pressure equilibrium. Now, vaporization is a transition of a liquid to a gaseous phase. So what will happen is the molecules on the surface of a covalent liquid will escape. They'll gain enough kinetic energy from, for example, the heat energy around them, and that'll get transferred into kinetic energy, and they'll change phase from liquid to gas, and they will diffuse or escape from that surface. So this process, when it happens below the boiling point, is called evaporation. So the particles at the surface of a liquid overcome the intermolecular forces of attraction and escape. So for example, those H2O molecules, when they evaporate, they overcome the hydrogen bonds. Now, condensation is the reverse. That's when the gas particles turn back into a liquid. So if I were to put some liquid into a sealed container, there would be liquid turning into vapor and vapor turning into liquid. So we've got vaporization or evaporation happening at the same time as condensation. Now, those vapor particles or gas particles will actually exert a pressure against the walls of a container, and we measure that in kilopascals. So if there's a lot of evaporation, of course, there's going to be a lot of vapor pressure. So after a while, those two rates will even out. So the rate of evaporation and the rate of condensation will form equilibrium. And so we use this little arrow. I don't think I've shown that to you before, so that's a two-ways arrows, just saying there's an equilibrium happening, that the rate of evaporation and rate of condensation, they're going backwards and forwards. So the point here is that the stronger the intermolecular bond, the harder it is for the particles to evaporate, because remember, evaporating is a molecule or a particle gaining enough heat energy, turning that into kinetic energy and escaping those intermolecular bonds. So the stronger the intermolecular bond, the lower the vapor pressure, because there's going to be less vapor particles evaporating. Here we have four different molecules. We've got propanone, we've got ethanol, water, and ethanoic acid. Now, ethanoic acid is the biggest molecule here, so CH3COOH. So we often know that as acetic acid or vinegar as well. And it's got the lowest vapor pressure. And what else do we need to think about? Let's think water here. Water boils at 100 degrees Celsius. So the boiling point is when the vapor pressure equals the atmospheric pressure in this case. So ethanol or methylated spirits should boil at 80 degrees Celsius, and propanone should boil at 55 degrees Celsius. That is at 1 atmosphere. So, you know, for example, on Mount Everest, water would boil at a lower temperature because it's got a lower pressure. So you're just reading down that curve there. So I could say, okay, if there's a vapor pressure of 90 kPa, for example, you can see that it would boil at 95 degrees Celsius. So at no pressure, water would boil. So out in space, water would boil because there's pretty well no pressure. What's the point of this lesson? The boiling point is when the vapor pressure equals the atmospheric pressure. Vapor pressure increases with temperature, and you think about that. You're increasing the heat energy, so you're increasing the kinetic energy in the liquid phase of the particles. They're going to escape the surface of the temperature, turn into a vapor, and put a greater pressure along the walls of a sealed container. Now let's have a look at melting and boiling points as well. We've got 3 molecules here. We've got propane, methoxymethane, and ethanol. Now they all have pretty similar relative atomic mass, or a molecular mass or molar mass, but their melting and boiling points are a little bit different. So let's think about why that is the case. So first of all, propane, that's quite a linear molecule. So it's a carbon chain. We've got a 3-carbon chain, and we've just got single hydrogen bonds on it. So it's just going to be a non-polar molecule. So wherever you see an ane, you just know it's a carbon chain with single bonded hydrogens onto the carbons, and they're pretty well linear molecules, and they're going to be non-polar. So it's going to have quite a low melting point and a low boiling point. So remember, it would form a solid then at negative 189 degrees Celsius. So quite a low temperature to turn propane into a solid. But propane turns into a liquid, or turns into a gas, at negative 42. So there's only one sort of intermolecular force acting on propane molecules, and they will be the dispersion forces. Now, the next one is methoxymethane. So we've got this oxygen in the middle, and we've got a couple of CH3s joined to it, essentially. So we've got a methyl group, which is like a methane, and we've got a methane. So it's 2 methane molecules, but you pull off the hydrogen atoms and join them with an oxygen just to get that one. But you can see there's a couple of lone pairs there. So we're going to have some dipole interactions. The next thing we want to have a look at is the hydrogen bonding. And so you can see that in ethanol, we're going to have some hydrogen bonding occurring. So we should expect a higher boiling point. So metho, or ethanol, should boil away at 78 degrees Celsius. Now we can also consider the solubility of polar and non-polar substances. So remember the rule, like dissolves like. So for example, a non-polar solute, for example pentane, will dissolve in a non-polar solvent, for example octane. Now octane is going to be the more dense because it's the bigger molecule in this case, so we can think about that as the solvent, and this can be dissolved into it. Now a polar solute will dissolve into a polar substance. So water is the universal solvent, but it is polar in nature. So water dissolves most things, but it won't dissolve non-polar substances. Another one is alcohol. So things can be dissolved into alcohol, and so a number of medicines are. Now, if substances are miscible, it means that they mix pretty well and they dissolve in each other in proportions. If something is immiscible, it's liquids that are insoluble in each other. So for example, oil and water are immiscible because remember, oil is a hydrocarbon and it's a non-polar substance, whereas water is the polar solvent. So today we looked at the vapor pressure and solubility of covalent molecules based on their intermolecular forces. When you're confident you understand that, have a go at the mastery questions, please.